at Moccasin. The objective of the process is to design a cost-effective unit to minimize the odor emanating from Moccasin Bend, and it's causing North Chattanooga not to smell too pleasant, especially this time of year when it gets warmer. It doesn't smell too good. But the units we're going to be using to kind of simplify everything as far as the odor coming out is we're just going to assume that a majority of the odor is hydrogen sulfide because that is where a majority of the odor comes from. The majority of the complaints are with the rotten egg smell that you get from hydrogen sulfide. So we're going to say a majority of the odor came from the primary clarifier and the headworks, and we're going to use a basis of 12,000 cubic feet per minute for the primary clarifier, 6,000 for the headworks, and assume 10 parts per million hydrogen sulfide from the primary clarifier and 15 from the headworks. So we're going to cap off these two units, the primary clarifier and the headworks, and we're going to send the odor through one of the 4 treatment units, being a chemical scrubber, biological scrubber, and basically the 2 of these work by sending the foul air through some sort of solution that will remove the odor, or else a filter device, whether it be a physical filter as a carbon absorber or a biofilter, which it works with different types of bugs, I guess you could say, to simplify everything. But the chemical scrubber works by taking the molten hydrogen sulfide and reacts it with sodium hypochlorite and sodium hydroxide to solidify this sulfur. It also makes salt water. But goes through, and the foul air comes here through the bottom, where the liquid recycle is dribbled down through a medium, and the clean air is absorbed through this and is recycled, and the clean air comes out the top. We looked through many different alternatives and came up with a Venturi scrubber. Venturi scrubber, just kind of the shape of it, is almost like it gets wider as it goes up, and came up with a height of 13 3/4 inch and a width of 12 foot and 5 inches. And the kind of layout, the primary clarifier air and the headworks air will come in and will be mixed with this chemical screw as they go through the scrubber. Then it will be a 2-stage process. It will go through the first one, where about 80% of the hydrogen sulfide is removed, and the second one, where about remaining will remove about 99%. And then you've got your clean air here and your chemicals, which can be disposed of or recirculated here, whichever. And then the bioscrubber comes through, and the clean air comes in and goes through more of a biological medium and is kind of recycled around. And as far as sizing and whatnot, the same size scrubber can be used for both chemical or biological scrubbers. The biofilter, the foul air comes in and goes through an organic medium. It can either go through the bottom and come out the top, or from the top throughout the bottom. It doesn't particularly matter which way it flows. But the 2 main types you see are soil, or more like a mulch type of bed. And when we did it, basically what you want is a retention time. You want your retention time to fall between 2 medium, depending on if you're using more of an organic medium or a soil medium. And then you want your loading rate to fall between certain variables. And when we did this, came up with a depth, either 165 feet or 165 with the organic medium, or this 100 feet with the soil, about 50 kind of square with the length and the width, and 75 with the soil. So I don't know, that's pretty steep, so might not be the best alternative of the 4. And then Jackie's going to dive into a little bit about how the kind of carbon absorbers work and cover some more detailed calculations about that.
Okay, so with the carbon absorber, you have the dirty gas coming through. It goes to the carbon bed. The carbon bed will absorb the hydrogen sulfide. Now we have the clean gas. The thing about this is this will, eventually you'll have to replace the carbon bed. So that's something we're kind of looking at that could be a problem for our customer. So some constraints. Arcadis was the people we originally got our information from, and some constraints you're going to run into for any company is obviously cost, but then the bed depth. According to site specifications, it has to be less than 3 feet. And for the carbon absorber to be economical, the diameter needs to be less than 12 feet, and that's for transportation reasons. And carbon selection, we're not really familiar with what type of carbon, that you have different grades you can put in there, so we're looking at different options. So some calculations. As previously stated, we have to have about, for it to be economical, there needs to be a 12-foot diameter maximum. The site isn't allowed for more than a 3-foot bed depth. So when we did some calculations, if I did 12 feet, I got a 3.5 bed depth. Well, according to our constraints, we can't have that. So a solution was to have 2 beds at 12 feet diameter at approximately 1.8 feet depth, or 2. We can give the numbers. The depth can be a little bit bigger as long as we just need to make sure it has enough room for the carbon to go through and the different layers. So what we need to do in the long run is we need to figure out how much fiberglass we're going to need for the carbon absorber and calculations for the fan and how much stainless steel we're going to need. Those are the cost calculations left we have to do. And so talking about our customer needs again, so left for some more calculations and stuff. So talking about, we can talk about maintenance and replacing costs. I found some numbers on the internet saying that activated carbon is approximately $1,000 a ton. I don't know how accurate that is. We're going to do some more research. And this was based on generic cost. So from this, looking at our customer needs, according to Arcadis, the carbon absorber was most effective at the pumping station for the wet wells. But when we looked at the initial information, this was less than 1% of our odor cause. So when we're looking at our final, we're going to make sure that the solution takes care of the most odor, removes the most odor as possible for the cost. So in summary, the odor coming from the plant is about 76% from the primary clarifiers and about 1.5% from the odor outlet. So our solution needs to address the biggest part, which is the 76% from the primary clarifiers. In conclusion, we're currently working on finding the most cost-effective, customer-friendly maintenance-wise, and not only for like when they're replacing any parts they need to do, but for the long run. And we need to do remaining cost calculations and do some final size calculations.